In the name of Almighty God, I'm Mahsa Sankosha, and today I want to talk about Hartmann flow in liquid metal blanket with heat transfer. The Hartmann number, or HA, is the ratio of electromagnetic force to the viscous force, first introduced by Julius Hartmann (1881 to 1951) of Denmark. It is frequently encountered in fluid flows through magnetic fields. It is defined by Hartmann flow is equal to Bl multiplied by Q divided by mu to the power of 1 divided by 2, where B is the magnetic field intensity, L is the characteristic length scale, sigma is the electrical conductivity, mu is the dynamic viscosity. And nuclear fusion. Nuclear fusion is a reaction in which two or more atomic nuclei combine to form a large nucleus. The difference in mass between the reactants and product is manifested as either the release or the absorption of energy. This difference in mass arises as a result of the difference in nuclear bonding energy between the atomic nuclei before and after the fusion reaction. Nuclear fusion is the process that powers all active stars via many reaction pathways. Fusion processes require an extremely large triple product of temperature, density, and confinement time. These conditions occur only in stellar cores, advanced nuclear weapons, and are approached in fusion power experiments. A nuclear fusion process that produces atomic nuclei lighter than nickel-62 is generally exothermic due to the positive gradient of the nuclear bonding energy curve. The most fusible nuclei are among the lightest, especially deuterium, tritium, and helium-3. The opposite process, nuclear fission, is most energetic for very heavy nuclei, especially the actinides. Applications of nuclear fusion include fusion power, thermonuclear weapons, boosted fission weapons, neutron sources, and super heavy element production. Chemist William Draper Hawkins was the first to propose the concept of the nuclear fusion in 1915. Francis William Aston's 1919 invention of the mass spectrometer allowed the discovery that four hydrogen atoms are heavier than one helium atom. Thus, in 1920, Arthur Eddington correctly predicted fusion of hydrogen into helium could be primarily source of stellar energy. Quantum tunneling was discovered by Friedrich Hund in 1927 with relation to electron levels. In 1926-28, George Gamow was the first applied tunneling to the nucleus. First to alpha decay, then to fusion as an inverse process. From this, in 1929, Robert Atkinson and Fritz Hartmann made the first estimates for stellar fusion rates. In 1938, Hans Bethe worked with Charles Crutchfield to enumerate the proton-proton chain that dominates Sun-type stars. In 1939, Bethe published the discovery of the CNO cycle common to higher mass stars. Early experiments during the 1920s, Patrick Blackett made the first inclusive experiments in the artificial nuclear transmutation at the Cavendish Laboratory. There, John Cockcroft and Ernest Walton built their generator on the inspiration of Gamow's paper. In April 1932, they published experiments on the reaction of the specific lithium proton and helium, where the intermediary nuclide was later confirmed to be the extremely short-lived beryllium. This has a claim to the first artificial fusion reaction. In papers from July and November 1933, Ernest Lawrence and his colleagues at the University of California Radiation Laboratory in some of the earliest cyclotron experiments accidentally produced the first deuterium fusion reactions. Under radiation lab only detection, the resulting energized protons and neutrons misinterpreted the source as an exothermic disintegration of the deuterons, now known to be impossible. In May 1934, Mark Oliphant, Paul Harteg, and Ernest Rutherford at the Cavendish Laboratory published an intentional deuterium fusion experiment and made the discovery of both tritium and helium-3. This is widely considered the first experimental demonstration of fusion. In 1938, Arthur Rowling at the University of Michigan made the first observation of deuterium-tritium DT fusion and its characteristics for 14 megavolts neutrons, now known as the most favorable reaction. The release of energy with the fusion of light elements is due to the interplay of two opposing forces. The nuclear force, a manifestation of the strong interaction, which holds protons and neutrons tightly together in the atomic nucleus, and the Colombo force, which causes positively charged protons in the nucleus to repel each other. Lighter nuclei smaller than iron and nickel, are sufficiently small and proton-poor to allow the nuclear force to overcome the Coulomb forces. This is because the nucleus is sufficiently small that all nucleons feel the short-range attractive force at least as strong as they feel the infinite-range Coulomb repulsion. Building up nuclei from lighter nuclei by fusion releases the extra energy from the net attraction of particles. For larger nuclei, however, no energy is released because the nuclear force is short-range and cannot act across larger nuclei. Fusion powers stars and produces most elements lighter than cobalt in a process called nucleosynthesis. The Sun is a main sequence star and as such generates its energy by nuclear fusion of hydrogen nuclei into helium. In its core, the Sun fuses 620 million metric tons of hydrogen and makes 616 million metric tons of helium each second. The fusion of lighter elements in stars releases energy and the mass that always accompanies it. For example, the fusion of two hydrogen nuclei to form helium, 0.645% of the mass is carried away in the form of kinetic energy of an alpha particle or other forms of energy such as electromagnetic radiation. It takes considerable energy to force nuclei to fuse, even those of the lightest element, hydrogen, when accelerated to high enough speeds. Nuclei can overcome this electrostatic repulsion and be brought close enough such that the attractive nuclear force is greater than the repulsive Coulomb force. The strong force grows rapidly once the nuclei are close enough, and the fusion and fusing nucleons can essentially fall into each other, and the result is fusion. This is an exothermic process. Energy released in most nuclear reactions is much larger than in chemical reactions because the binding energy that holds a nucleus together is greater than the energy that holds electrons to a nucleus. For example, the ionization energy gained by adding an electron to hydrogen nuclei is 13.6 electron volts, less than 1 millionth of 17.6 megavolts released in the deuterium tritium DT reaction shown in the agent's diagram. Fusion reactions have an energy density many times greater than nuclear fission. The reactions produced for greater energy per unit of mass, even though individual fission reactions are generally much more energetic than individual fusion ones, which are themselves millions of times more energetic than chemical reactions. While the mass energy equivalence fusion yield a 0.7% efficiency of reactant mass into energy. This can only be exceeded by the extreme cases of the accretion process involving neutron stars of black holes, approaching 40% efficiency, and antimatter annihilation at 100% efficiency. The complete conversion of 1 gram of matter could expel 9 multiplied by 1013 joules of energy. In astrophysics, fusion is responsible for the astrophysical production of the majority of elements lighter than iron. This includes most types of Big Bang nucleosynthesis and stellar nucleosynthesis. Non-fusion processes that contribute include the process and SR process in neutron merger and supernova nucleosynthesis, responsible for elements heavier than iron. Stars. An important fusion process is the stellar nucleosynthesis that powers stars, including the Sun. In the 20th century, it was recognized that the energy released from nuclear fusion reactions accounts for the longevity of stellar heat and light. The fusion of nuclei in a star, starting from its initial hydrogen and helium abundance, provides that energy and synthesizes new nuclei. Different reaction chains are involved depending on the mass of the star and therefore the pressure and temperature in its core. Around 1920, Arthur Eddington anticipated the discovery and mechanism of nuclear fusion processes in stars. In his paper "The Internal Constitution of Stars", at that time the source of stellar energy was unknown. Eddington correctly speculated that the source was fusion of hydrogen into helium, liberating enormous energy. According to Einstein equation is equal to mass multiplied by c to the power of 2. This was particularly remarkable development since at that time fusion and thermonuclear energy had not yet been discovered, nor even that stars are largely composed of hydrogen. Eddington's paper responded that the first one is the leading theory of stellar energy. The contraction hypothesis should cause the rotation of a star to visibly speed up due to conservation of angular momentum. But observations of Cepheid variable stars showed this was not happening. The only other known plausible source of energy was conversion of matter to energy, and Einstein had shown some years earlier that a small amount of matter was equivalent to a large amount of energy. Francis Austin had also recently shown that the mass of a helium atom was about 0.8% less than the mass of the four hydrogen atom, which would combined form a helium atom according to the prevailing theory of atomic structure, which held atomic weight to be the distinguishing property between elements. Work by Henry Moseley and Antonius van den Broek would later show that nucleic charge was the distinguishing property, and that a helium nucleus therefore consisted of two hydrogen nuclei plus additional mass. This suggested that if such a combination could happen, it would release considerable energy as a byproduct. If a star contained just 5% of fusible hydrogen, it would suffice to explain how stars got their energy. It is now known that most ordinary stars are usually made of around 70% to 75% hydrogen. Further elements might also be fused, and other scientists had speculated that stars were the crucible in which light elements combine to create heavy elements. But without more accurate measurements of their atomic masses, nothing more could be said at that time. All of these speculations were proven correct in the following decades. The primary source of solar energy and that of similar-sized stars is the fusion of hydrogen to form helium, the proton-proton chain reaction, which occurs at a solar core temperature of 14 million Kelvin. The net result is the fusion of four protons into one alpha particle, with the release of two positrons and two neutrons, which changes two of the protons into neutrons, and energy. In heavier stars, the CNO cycle and other processes are more important. As a star uses up a substantial fraction of its hydrogen, it begins to fuse heavier elements. In massive cores, silicon burning is the final fusion cycle leading to a build-up of iron and nickel nuclei. Nuclear binding energy makes the production of elements heavier than nickel via fusion energetically unfavorable. These elements are produced in non-fusion processes. The S process and R process and the variety of processes that can produce p nuclei. Such processes occur in a giant star shell, or supernova or neutron star mergers. And what about the brown dwarf? Brown dwarf use deuterium and in a very high mass cases also fuse lithium. And about white dwarf, carbon oxygen, white dwarf, which accrete matter either from an active stellar companion or white dwarf merger, approach the Chandrasekhar limit of 1.44 solar masses. Immediately prior, carbon-burning fusion begins, destroying the Earth-sized dwarf within 1 second. Much more rarely, helium-white dwarf may merge, which does not cause an explosion but begins helium burning in the extreme type of helium star and neutron star. Triple alpha process in neutron stars. Some neutron stars accrete hydrogen and helium from an active stellar companion. Periodically, the helium accretion reaches a critical level and thermonuclear burn wave propagates across the surface on the timescale of 1 second. And what about the black hole accretion disks? similar to the stellar fusion. Extreme conditions within black hole accretion disks can allow fusion reactions. Calculations show the most energetic reactions happen around lower stellar mass black holes below 10 solar masses compared to those above 100. Beyond the Schwarzschild radiocarbon burning and fusion of helium-3 dominates the reaction. Within these systems, around lower mass black hole, fusion of nitrogen, oxygen, neon, and magnesium can occur. In the extreme limit, the silicon burning process can begin with the fusion of silicon and selenium nuclei. From the period approximately 10 seconds to 20 minutes after the Big Bang, the universe cooled from over 100 kilovolts to 1 kilovolt. This allowed the combination of protons and neutrons in deuterium nuclei and beginning a rapid fusion chain into tritium and helium-3 and ending in predominantly helium-4 with a minimal fraction of lithium, beryllium, and boron nuclei. Observational evidence shows that packets of gas in the early universe became thick to collapse under their own gravity. This activated nuclear fusion with the formation of the first stars around 13.6 billion years ago. A substantial energy barrier of electrostatic forces must be overcome before fusion can happen. At larger distance, two nuclei repel one another because of the repulsive electrostatic force between their positively charged protons. If two nuclei can be brought close enough together, however, the electrostatic repulsion can be overcome by the quantum effects in which nuclei can tunnel through Coulomb forces. When a nucleus, such as a proton or neutron, is added to a nucleus, the nuclear force attracts it to all the other nucleons of the nucleus, if the atom is small enough, but primarily to its immediate neighbors due to the short range of the force. The nucleons in the interior of nucleus have more neighboring nucleus than those on the surface. Since smaller nuclei have a larger surface area to volume ratio and the binding energy per nucleon due to the nuclear force generally increases with the size of the nucleus but approaches to a limiting value corresponding to that of a nuclei with a diameter of about 4 nucleons. It is important to keep in mind that nucleons are quantum objects. So, for example, since two neutrons in a nucleus are identical to each other, the goal of distinguishing one from the other, such as which one is in the interior and which is on the surface, is in fact meaningless, and the inclusion of quantum mechanics is therefore necessary for proper calculations. The electrostatic force, on the other hand, is an inverse square force to a proton added to a nucleus will feel an electrostatic repulsion from all the other protons in the nucleus. The electrostatic energy per nucleus due to the electrostatic forces thus increases without limit as nucleus atomic number grows. The net result of the Opposing electrostatic and strong nuclear forces is that the binding energy per nuclei generally increases with increasing size up to the elements iron and nickel and decreases for the heavier nucleus. Eventually, the binding energy becomes negative and very heavy nucleus with more than 208 nucleons corresponding to a diameter of about 6 nucleons are not stable. The four most tightly bound nuclei in decreasing order of binding energy per nucleus are 62. Even though the nickel isotope 62 nickel is more stable, the iron isotope 56 of freon is an order of magnitude more common. This is due to the fact that there is no easy way for stars to create 62 nickel through the alpha process. An exception to this general trend is the helium-4 nucleus, whose binding energy is higher than that of lithium, the next heavier element. This is because protons and neutrons are fermions, which according to the Pauli expulsion principle cannot exist in the same nucleus in exactly the same state. And here we can see that we have a geometry in computer simulation, and you can see inside this rectangle by the increasing or decreasing the transparency. The material that we have used is a lithium 200 degrees of centigrade, and the physical module are about heat transferring fluid, laminar fluid, and magnetic and electric fields. And finally, you can see the magnetic flux density in this Hartmann blanket flow, and also in the another section, electric field and fluid velocity, temperature, and the last but not least is the temperature. Thank you so much for watching my video until the end, and also you can download it from github.com/masterscript.